I spent like 80% of my time.
Yeah, any questions from last time?
Dr. Kovenal,
Mhm.
on the homework, and the, for two, B, where you asked about a field with a unique quadratic extension and one without. Are these fields that, like, are the typical example that you're thinking of that we should respond with? Are they like fields that we should be comfortable with, or like know ahead of time?
Well, there is not a unique answer to either
Right,
one of those questions, but I can think of something that's pretty familiar.
Okay.
So let me remind you of this terminology that we were using last time. So if we have A and E and F fields and H, a subgroup of the Galois group of F over K, then H prime. So when you prime a group, it turns into a field. So this is the collection of V and F, such that sigma V is equal to V for all sigma in H. And E prime, this should be a group. So this is the sigma in G. So I don't have to write down one group all the time. So that's a sigma in G such that sigma E equals E for all E and E. And remember, we call H prime the fixed field of H. So I pointed out last time, the last thing that we talked about was that one prime is all of F, right? Because one is, okay, that's a group, right? And so one prime is everything in F such that one V equals V, so that's everything, right? Because the identity homomorphism leaves everything alone. On the other hand, not necessarily true. That G prime equals K. In fact, we gave an example where it was bigger. So for example, if K equals Q contained in Q radical, or I'm sorry, not radical, Q root of 2, F, then G is equal to 1. Right? Because if you're looking at automorphisms of Q adjoined with the Q root of 2, then fix Q, well, think to yourself, where can I take the cube root of 2? And I can only take it to one of the other roots of this polynomial. But the other two are complex and not real, right? So you're forced with taking the real root to itself. And once you take that to itself, that determines everything, and it's the identity automorphism. And so in this case, G prime equals 1 prime, which is all of F, which of course strictly contains K. All right. And this, I bring this example up again because this is the definition of Galois. Definition. Looking at the fields. If I will end up, let's see, G is the Galois group, F over K. If K is the fixed field of G, we say F is Galois over K. So if the fixed field, so if the subfield of F that is fixed by every automorphism in G. If you look at every automorphism of F that fixes K, certainly K is contained in the fixed field just by definition, because all those automorphisms fix K. So if you look at the field determined by everything that's fixed by every automorphism, if that's only K, then we say that F is Galois over K. And if not, we say that F is not Galois. Let me give you a kind of working way to do it. Equivalently, F is Galois over K if for all alpha and F minus K. So if I pick an arbitrary element of F that doesn't live in K, there exists sigma in the Galois group of F over K, such that sigma alpha is not equal to alpha. So if every element of F that isn't already in K can be moved by some automorphism, we say it's Galois. This strikingly shows up here because in this example here, the Galois group of this big thing over Q is just the identity. And notice that no element in here that's not in, no element in this thing is moved at all. Every automorphism fixes it because the only automorphism is the identity. Okay. Let me give you kind of a example here. Let D be a square free integer. So and consider K equals Q and F is Q joined with the square root of D. Let me recall for you, just in case it's a little fuzzy, square free integer means that the only square integer that divides D is 1. So for example, 1 is not square free, 4 is not square free, 12 is not square free, -1 is. Right? By the way, anybody want to suppose why I focus on this being a square free integer? What could happen if D was not square free? What if D was, say, 4? What can you say about this extension here?
In the same field.
It's the same field, right? So the whole purpose of this is to make sure that this extension actually is of degree 2, right? And in fact, what it means is x squared minus D is irreducible. And actually cuts out some redundancies because remember, let me point out that if D was something like 12, which is not square free, notice the 12 is divisible by 4. So Q adjoined with the square root of 12 is the same thing as Q adjoined with 2 times the square root of 3, which is the same thing as Q adjoined with square root of 3. So I might as well have just done 3 in the first place. All right. Okay, notice that the degree yes.
So x squared minus D is irreducible in QX.
Yeah.
Okay.
Yeah, certainly. It's not irreducible in the bigger field.
Sure,
That's
yeah,
the whole
okay.
point, right? Right. So by the way, extensions of degree 2 are almost always Galois. Not always, I can come up with exception, but we'll talk about that later. In characteristic 0, extensions of degree 2 are always Galois. And I'm gonna basically show you that here. So notice that Q square root of D, this is a set of elements in the form A plus B radical D, where A, B are in Q. Agreed? Well, let's suppose. Well, what are the automorphisms? Well, we've talked about this example before. Notice that the Galois group of Q radical D over Q is isomorphic to Z mod 2Z. Right? And there are two automorphisms, the identity and what you might call conjugation. Right? The identity of A plus B radical D is A plus B radical D. And you have conjugation sigma of A plus B radical D is A minus B radical D. Actually, if I wanted to be mean to the younger undergraduates, I might actually write this function down and say, prove that this is an automorphism, right? It's not hard, but it's obnoxious, right? Because nobody wants to multiply A plus B radical D times C plus F radical D, multiply it out, and yuck, it's a terrible mess. But we are more sophisticated. This is an automorphism because it takes the root of this polynomial. The polynomial here will be x squared minus 2ax plus, right, plus a squared minus db squared, right? It takes that polynomial, this root to the other root. We already know that when you have an algebraic element, then these are two roots of the same polynomial, so their field extensions are the same, they're in the same thing, so this is actually an automorphism. But you might just see what a pain in the butt it is to check that kind of by hand. These are the two automorphisms. Why is it Galois? Well, select alpha in Q radical D minus Q. Now, if it's not in Q, what this means, what is this condition? Alpha is in Q radical D minus Q. What is that equivalent to saying?
B is not 0.
That B is not 0. Fine. And so, notice that sigma alpha is A plus B, I'm sorry, A minus B radical D, which is not equal to A plus B radical D. So sigma alpha is not equal to alpha. So F is Galois. Okay.
What do you mean, like, they're not equal, but that equals?
So,
Oh, which is not equal
sigma-
alpha, okay.
right. So in other words, I've shown that I can move everything that's outside of Q, so I'm good to go. It's Galois, right? Any questions on that? Okay, so let me make a remark here. This is a remark, so this is a spoiler. We're gonna talk about this a little bit later, but I wanna give you kind of a look ahead, because I think it's kind of good to see where we're going. And what I consider to be an important consequence of where we're gonna go. Suppose I think it's very natural to ask, because I like simple things, right? Suppose I walk up to you and give you a field K. The easiest kind of extensions of K are the simple ones, K of U, just take some element and join it, right? If that U is transcendental, then that looks like rational functions, right? If it's algebraic, then this is an interesting extension, and it's very natural to ask, okay, if I have a field K and I join U to it, and U is algebraic, when's it Galois? So I'm gonna give you some, conditions, and we'll talk about this in the sequel. So here's a look ahead. So spoiler, if you will. Let K be a field. And f of x, an irreducible polynomial. In Kx. And U a root of fx. Okay, so I've got a field, I've got an irreducible polynomial, call it f of x, and then I've got some root of it. When is K U Galois over K? And I'll say something about this as well in a moment. There's a couple of conditions you need. F of x is a separable polynomial. I haven't defined this yet, but I'll tell you briefly what it means. It means all roots of f of x are distinct. And this is always true. True if characteristic K is 0. And it's sometimes true in characteristic P, but you got to be more careful. Now be careful here. I'm not saying that any polynomial in Kx has all different roots, because all I have to do is look at x to the 10th, right? It's got multiple roots, right? But remember, I'm assuming that this is irreducible. So what it means to be separable, what it means for a polynomial to be separable is it means that if you look at a field extension where it's got all its roots, all those roots turn out to be different, right? If you have a irreducible polynomial in characteristic 0, always true. Yes.
So does that also mean that f of x factors into linears?
It factors into linears in some extension.
Okay.
Right, but yes, here, that's the second thing.
Oh.
2. KU contains all roots of fx. This isn't guaranteed in general. Now, let me point out, I want to connect this up with the previous example. In the previous example, what did I look at? I looked at this extension here. Do I agree with that? Well, if you believe my yammerings on about characteristic 0, in this example here, then the minimal polynomial x squared minus d, it has, it's separable. Right. And actually, look at the two roots of this polynomial. Radical D and minus radical D. Those two are different, by the way, except in characteristic two, right? Because radical D and minus radical D could be the same in characteristic two, right? In characteristic zero, they're gonna be different. And when I join this root here, it contains all the roots, right? Because in the quadratic formula, what happens? You have, I can't believe I'm having to repeat the quadratic formula here. But here we have, let me just make it monic because I am a simple creature. Well, these can be rational numbers. Right. The B over two is already in the field. Again, unless characteristic zero, that could be a problem. The B over two is in the field. And when you adjoin the root here in that special case, you'll get this radical is in the field too. So when you divide by two, it is. So if the radical's in the field, when you change the sign, it's got to be in there, right? And so that's what two is kind of unfair in a certain sense, right? Let me give you an example, kind of a non-example here. If you look at the polynomial, and it gets worse actually. K equals Q, and polynomial f of x is x cubed minus 2. And you let u equal the cube root of 2. We've seen this is in Galois, and the problem is the separability criteria is not an issue because it's characteristic zero. Does not have all roots. So the QU is not Galois, right? The smallest field that does have all the roots is this. Remember this one we looked at where this is the cube root of 2 and this is the current cube root of n. The degree of this extension is 6. This is actually equal to QU. Well, let me say QV. For some V. But the polynomial is degree 6. Right? And so you'd have to hunt around for that. And it gets worse, right? I mean, I could, so if you look at, for example, if I up the voltage here, and we're going to go over these examples actually in more detail when we develop more tools, but again, this is kind of looking ahead at some of the things that can happen. And here I'll let u equal fifth root of 2. Then the degree of QU over Q is 5, and QU is not Galois. And so here's actually what happens. What you can do is you can throw in the fifth root of unity, but there's no way that contains all 5 roots of that polynomial because all of them are non-real complex except for the fifth root of 5, right? Actually, to get the whole thing, you now take Q of U and you adjoin, tornado, where this is so tornado is E to the I, 2 pi over 5. But once you stick this on, that is, all you need is one more root. The jump is only 4, and now you've got all the roots. As a matter of fact. So the degree of this extension here, as opposed to the 6 we got here, is 20. And that's the smallest one that contains all the roots. But this one is at Galois because it doesn't contain all the roots. And it gets worse. Because what happens here is you get a bargain. When you adjoin one root, it takes you a jump 5. If you adjoin one more root of this, any of the other 5 roots, you automatically pick up the rest, right? Because what happens is you will now have the real 5th root of 5, and then you'll have the 5th root of 5 times some primitive 5th root of 1. The quotient will give you that primitive 5th root of 1. So you're going to have every 5th root of 1 in this next jump, which means you get all the roots, right? But here's what could happen. And in fact, let's see, I think it's the truncated exponential. It turns out that if you have 1 plus x plus 1/2 x squared plus 1/6 x cubed plus 1/24 x 4 plus 1 over 120 x 5. Y'all see where I get this? It turns out, we're going to compute Galois groups later, that if you use the truncated exponential degree in, I think it's got, I'm going to look this up to be sure I'm not blowing smoke, but my recollection is that has Galois group SN. So what happens here is, let U1, U2, U3, U4, and U5 be the roots. If you look, you can take it as, believe me now, that this is actually an irreducible polynomial. So this jump is 5. In this field, this thing is no longer irreducible because what have I done? I've stuck on a root, right? That means in this field, this polynomial is x minus u times f1 of x. And it turns out this f1 of x of degree 4 is in fact irreducible. So now to get to the next root, you jump 4. Now in this field, f of x is x minus u1, or let's see, yeah, I'm at u equals u1, x minus u2 times f2 of x. This is degree 3 and also irreducible. This is u1, u2. And it keeps going like this. U1, U2, U3, U1, U2, U3, U4, U1, U2, U3, U4, U5. It turns out this jump is 3. This jump is 2. And yes, of course, this jump is 1, so I didn't need to make this last jump. But if you think about it, once you've got 4 roots, you have to have the 5th root. And the reason is the constant term of this, in this case 1, is the product of all the roots. Well, actually, it's minus the product of all the roots. So if you've got 4 of them, then that means you've got the reciprocal of the last one, so you've got the last one. So actually, to get all the roots, this is an extension of degree 120. So this is a worst case scenario. You join a root and your polynomial breaks down as small as it possibly can, right? And you just keep going. So it turns out that this field actually here is Q adjoined with W for a single element. Good luck. Good luck finding it. Its minimal polynomial will be of degree 120. And all 120 of those roots will be in this field. Right? So, yes,
So for that one, is QV, that one is, Galois over K?
my point here is this thing right here is, this thing, yes, this thing right here is Galois over Q. Right, or K, yeah, whatever you want to call it. And my point here is you can actually write this extension here. We're going to prove this later. You can write this extension, which I need two things to do, as a simple extension.
Dr. Florino.
Mhm.
And also that Q of adjoint W is also Galois over Q.
Yes, this is time, because what happens, it turns out that this is kind of the standard way to get a Galois extension. It turns out, again, this is looking ahead a bit. It turns out that you can always build a Galois extension as follows. Start with a field, take an irreducible polynomial out of it. If that irreducible polynomial is separable, if all the roots are distinct, just take those roots and dump it into the field, right? Which is essentially what we did here. We took the 5 roots and dumped it in there, and it'll be Galois. Right, so that's kind of the standard way to do it.
Is C like are the complex numbers Galois over itself?
Any field is Galois over itself.
Okay.
Always, right? Because, well, kind of vacuously, right? Because if you look at the automorphisms of the field that fix the field, that's only the identity, right?
Okay.
And so it is by definition its own fixed field.
And the algebraic closure of any field is going to be Galois?
So if you have a field and you have its algebraic closure, no, because what you need is you need all the polynomials to be separable, right? Which isn't always the case, right? So for example, if you look, you would have problems with something like this. If you look at this extension here, well, actually, let's look at this extension. Before I send you off, did you have questions?
So the minimal, or I don't know if this is the right term, but the minimal polynomial, or not polynomial, field extension is n-1, the degree n-1? Or like because if you have the 4 roots adjoin.
Well, so what I did is I went up piecemeal. The first thing I know is I know that this polynomial is irreducible. I didn't prove that, but it is. This polynomial is irreducible. So if I take any root and adjoin it, since that polynomial is, that's a 5 jump. Now take this polynomial, because what I'm trying to do is I'm trying to build a field extension where I've got all of these, right? I find myself talking about splitting fields, which is later, but hey, that's okay. So you've got this 5th degree polynomial. I know it's got at least one root, right? Because that's what I did. I forced it, right? It's got a root here. So I know that this thing has now got a factor of x minus u1, whatever that root is. And whatever's left over is degree 4. Now that degree 4 polynomial might break down. It might have other linear factors. It might break down into 2 quadratics. But it turns out in this particular case, it stays irreducible. Now, if I want more roots of this, I've got to jerk it out of this because I've already got this part of the root, right? So I jerk one out of this, U2, and it reduces it further. And it turns out in this case, that's it. It goes down to a degree 3. And that's why this process continues. So actually at this stage right here is where I've actually got all the roots. Because when I've got, and maybe I wasn't clear about that. Let me prove that at the second to the last stage I've got it. That's why that last jump is a 1. Because this polynomial is equal to x minus u1, x minus u2, x minus u3, x minus u4 times x minus u5. Right, in the big field, agreed? Now notice that the constant term negative u1, u2, u3, u4, u5, right? But the constant term is also 1 because it's the constant term of x, right? This means that u5 is negative u1, u2, u3, u4 inverse. Right? So in this step right here, I certainly have u1, u2, u3, u4, because I've got, in fact, I've got them all separately, so I've got their product. And this is a field, so I've got the inverse and the minus. And so therefore, notice that u5 is also in here, right? And that's why this last jump is a 1, because that last polynomial is linear. Yes.
Oh, I was gonna say, is it also not because like your f subscript 4 is gonna be a linear polynomial and it has to be u5?
That's right, that's right.
So are they not, or like, does the other field contain, like, since it contains, like, are they not equal?
Yes, they are equal.
Oh, they are equal?
Yeah.
Oh,
Okay, other questions? All right. Oh, yeah, I remember what I was gonna do. Looks like K. Okay. This is an interesting example. And here's kind of the problem. This is, so I haven't talked about separability yet. I've just given you an informal definition, but this will illustrate why this gives you a problem. Let me point out that the degree of f over k is 2. Right? And here's why. Characteristic 2 is very important here. What does a typical element of well, let me actually, this isn't going to prove it, but let me point this out first. What happens when you square this? Well, I call this alpha. And alpha squared is equal to, liberally using the fact that this is characteristic 2, when I square this thing, I get a0 squared plus a1 squared x squared plus ak squared x2k b0 squared plus b1 squared x squared plus bm squared x2m. Right? Characteristic 2 is very important there. I don't have any cross terms, right? Everybody okay with that? And notice that this is in x squared. So in particular, what I've shown is this is in fact an algebraic extension. Yes,
Why do you not have cross terms?
because it's characteristic too. Right, so for example, I should have a 2A0, A1X, right?
Oh,
But
right.
2 is 0, right? So all the cross terms are dead. It's the freshman's dream, baby, alright? This shows that in fact, this is an algebraic extension. And also, notice that in fact, it's a simple extension. Because if you look at actually only need this. Well, actually, I can do round bracket because round bracket is square bracket because X is algebraic. Because actually, the smallest field that contains F2 in X is this. This is completely unneeded, right? So this is the degree of F2 X over F2 X squared, rational functions in X as opposed to rational functions in X squared, is 2. And in fact, if I had done that first, that would show in fact that this is an algebraic extension because it's finite, but it was more fun to square that stuff, I think. Now, is this Galois? Well, let's look at the Galois group.
Is that the degree equals 2 or or
Yeah, that's right.
Oh.
Yeah, the degree of the extension is 2. So, somebody, what is the minimal polynomial of X? Well, you know, I guess it must be the root of a polynomial of degree 2. Notice because of this fact right here, to determine any automorphism of F2 of X that fixes F2 of X squared, all I gotta tell you is where X goes, right? So that's all I need. That's the only information is what are my possibilities for where X can go, right? Other than itself, it can certainly go to itself. And that's why I need the minimal polynomial, because I need to know what are the other roots of this minimal polynomial, because those are the only places it can go. Anybody, I bet it's a quadratic polynomial.
It's just X squared
T squared
equals.
minus X squared. Notice that X is a root of this, because if I plug in X for T, you get 0. Notice this is a polynomial. Here are my variables T. This is a polynomial with coefficients in the smaller field, right? Because X squared is in the smaller field. But here's what's going to make you angry. It's going to make the blood boil. This is T minus X quantity squared. Right? So in the bigger field, this factors as a power of a single linear polynomial. So if B is in the Galois group of F2X over F2X squared, then phi of X must be X. There's no other root. You have to go to X. All right? And there you go. So the Galois group of F2X over F2X squared is the identity. So F2X is not Galois over this is a slightly different situation than we got. Remember when I put the cube root of 2 into the rationals? We solved the Galois problem a little bit by saying, okay, well, just throw in the rest of the roots. You don't have that option here because the minimal polynomial only has x as a root. There's nothing else to help you out. So this is what the problem's going to be. So coming full circle back to your original question, if you take the algebraic closure of this thing, you're still going to have this problem that persists here.
Right.
Okay, any questions on that? Any questions? Okay, I think I've just got time to do this. I'm going to state the fundamental theorem of Galois theory, and you can, put that pipe and smoke it. Oh, by the way, let me, actually, you know what? Yeah, I'm going to take some time to explain this instead of hurrying this up at the end of class. So let me just say something about the next couple of days. Some of you might even be volunteers, but the calculus challenge is coming up. So Friday, we will have class, but only on the exciting format that is YouTube. I will make some videos probably this afternoon. Well, good Lord willing, the creeks don't rise. I'll make the videos this afternoon and post them. So that's what Friday's class is going to be. If you all need office hours to talk about the homework, I have made Adam Price available to you all. He will be in his office in B04 from 10 a.m. till 4 p.m. on Friday. So was it?
Is that long haul?
It's in Long Haul. That's right. Also, I sent you all an email. I would presume, just correct me if I'm wrong, but I would presume that everybody's okay with starting the exam on Wednesday at 9 o'clock and then finishing at 10. How about a review session Monday at like 5? Okay, I'll get on that. Okay, any questions? Any questions? Okay. All right, we'll see you.